In this video, I want to go over the cross product, sometimes called the vector product. So the cross product between two vectors, A and vector B, you'll see it's sometimes written like this, where we use an X or a cross to indicate what type of product we're using between our vectors. So there are different types of ways you can multiply vectors together. And the reason why this is called a vector product is because the result gives a new vector. So when you cross two vectors, you get a new vector. So there's also a dot product, also called the scalar product. And when you multiply two vectors using a dot product, you get a scalar. So you don't get another vector. But when you do a cross product or a vector product, you do. And so what the cross product does is it multiplies perpendicular components of the two vectors. So perpendicular components of two vectors. And then it gives a new vector that is perpendicular to both of the original vectors. Okay, to both of them. So the first two vectors, you can think of them as lying in a plane. And then the new vector from your cross product is perpendicular to that plane. And the direction of this new vector is given by a right-hand rule. So if I draw kind of a plane, in this plane I may have my two vectors A and B kind of live in this plane. And then if I cross them, then I'll get a new vector that's perpendicular to both of them. And this is my vector C. And so the magnitude of vector C from my cross product is the magnitude of A, so I'll write this two ways, the magnitude of the first vector times the magnitude of the second vector times sine of theta, where theta is the angle between A and B. So angle between vectors A and B. So often when you see two things multiplied by each other times sine or cosine of some angle, that angle is always between the two things in front of it. Okay? And sometimes we want to write, instead of writing these absolute value bars, if we just dropped the vector hat or the vector arrow above our vectors, that also indicates we're only talking about magnitude. So this may also be written as just AB sine theta. So our right-hand rule for getting the direction of the cross product, also abbreviated RHR. In order to do this, you point your fingers, and you can use this example here if you want to go through it. Point fingers in the direction of A, or whatever your first vector is. Okay, so the order will matter, so point it in the direction of the first vector. And then you want to curl your fingers in the direction of B, or your second vector. And then your thumb will point in the direction of the new vector. So points in the direction of C. Vector C, or your new vector. Okay, so if you point your fingers across A and then curl them up kind of toward B, your thumb will be pointing perpendicular in the direction of C. If we want to actually get the direction of this new vector, then we often want to evaluate cross products with our vectors written in Cartesian form. So Cartesian vectors are written in the form, so vector A would be written in the form AX times I hat plus AY times J hat plus AZ times K hat. And so I hat, J hat, and K hat here are just our unit vectors. So we can write our vector b in the same way. The x component times I hat, the unit vector along the x direction, by times j hat, the unit vector along y, plus bz k hat, the unit vector along z. Okay, so now when we do our cross product, so our new vector c is equal to a cross b, this is going to equal ax I hat plus ay j hat plus az k hat cross bx I hat plus by j hat plus bz k hat. And the easiest way to evaluate this is just to distribute. So you end up getting quite a few terms. But if you do that, your magnitudes, ax and bx, those are not vectors, so they don't get crossed, they just get multiplied together. But I hat and I hat, j hat, and k hat, these are all vectors. They're unit vectors, but they're still vectors, so they get crossed. And then you get ax by, so I hat cross j hat, plus ax bz I hat cross k hat, and so on. And so these magnitudes, those are pretty easy. Those are just numbers that you multiply together. And then to get the direction of I hat cross I hat, or I hat cross j hat, and so on, is you go in a cyclical pattern. So you have I hat, and then after I hat you have j, so after x you have y, and you have z or k hat. Okay, and so as long as they go in this order, I hat cross j hat, you get the next one in line, k hat. Or j hat cross k hat gives you positive I hat. K hat cross I hat gives you j hat. Okay, if any of these are out of order, so you went I cross k or j cross I, you just pick up a minus sign. Okay, so that's called anti-cyclical. And that just means you get the same letter, but you pick up a minus sign in front. Okay, so the order matters with a cross product. And then what about I cross I, j cross j? Well, we said the cross product will multiply perpendicular components of two vectors, but if I is parallel to I, then it's not perpendicular to itself, it's in the same direction. So that just equals 0. There is no component of I that's perpendicular to I. It's in the same direction. So taking a cross product of a vector with itself will always give 0, where that's not true for a dot product. So what would you get if you were to distribute all of your terms like we saw previously? Well, you would get ay bz minus az by times I hat plus az bx minus ax bz j hat plus ax by minus ay bx k hat. Okay, so what I want you to notice is these are kind of cyclical. Okay, so first off, this is equal to some new vector c, so this corresponds, everything in front of I hat is your x component, everything in front of j hat is your y component, and everything in front of k hat is your z component. Okay, but if you look at these terms, there's nothing in the I hat component but z's and y's. There's nothing in the j hat component but z's and x's, and there's nothing in the k hat but x's and y's. Okay. Not only that, but the first term you always start with them in order. So I is only going to depend on y and z. So that means you start with y and then multiply by the z component of the other vector, and then they're in opposite orders on the next term. Okay, for the next one you have to go in order, so it's z times x, and then x times z. And then finally x times y, then y times x. And then for all of them, you also have a minus sign. Okay, so this is one of those things that if you do it enough, you can probably memorize it, but you don't have to. So these are cyclical, so I just want to put this. X goes, then y, then z, not x, then z, and then back to x again. Okay, so if you wanted to, you eventually get used to this and you can kind of remember it. But there's an easier way using some linear algebra, and even if you haven't had any linear algebra, you can learn how to do it pretty easily. You can put these vectors into a 3x3 matrix. So you put your unit vectors in the first row. You put your first vector and its components in the second row, so ax, ay, and az, and you put the second vector's components in the third row, bx, by, and bz. And so the way you take the determinant of a 3x3 is first you pick out a component on the top row, and then you cross out everything that's in that row and that column. Then you take the determinant of this 2x2, and the way you do that is you start with this first term in the top left, and you go like this. You go down and to the right. So this first term is going to be your I hat components, and you're going to do ay, and then down and to the right times bz, and then you're going to have a minus sign, and then you're going to go from the top right to the bottom left. So az times by. Okay, now let me erase this really quick and do the second component. Okay, so now we're ready for the second component. So we circle it, we cross out everything in that row and that column. And then we want to take the determinant of the next one in the same way, except notice now if we go from left to right, we go from x to z. That's not cyclical. We're supposed to go from x to y. So in order to account for that, we need to pick up a minus sign. Okay, so I'm going to put a minus sign in front of my j hat component. Okay, so now we can take the determinant like we normally did. We start in upper left, go to the bottom right, and then we go top right down to the bottom left. So this will be ax times bz minus az times bx. Okay, now I'll erase this and we can do our last component. So for the last component, we circle k, mark out everything in that row and that column, and then take the determinant of this. It's in order, so we get a plus sign, so plus our k hat term, and this will be ax times by, so ax by minus ay bx. So we went down and to the right, and then from the top right down and to the left. Okay? And so again, this minus sign comes from going from x to z, not x to x, but x to z. And if you look, these are in the opposite order as what we have at the top. So not this term. This is in the opposite order as what we have in the top. And that opposite order comes because there's a minus sign out front. Okay, and it's because we didn't go in order. But if you distribute that minus sign, then you'll find that we get the exact same thing as I have written above. Okay, and so just to show you what we're doing, if you have we're taking a bunch of little 2x2 determinants. So this is a little aside. If you have a determinant of a 2x2, a, b, c, d, the determinant of this, so call this a matrix M, the determinant of this matrix is equal to AD minus BC. And so you can kind of see that's what we've been doing. We did AD and then minus BC. We kept doing this over and over again. And so you can practice this until you get comfortable with it. It's in a lot of textbooks. And we'll be doing examples where we actually go through this and plug in some numbers. So now I want to talk about properties of the cross product. So the first thing, it is anti-commutative. So I kept saying that the order matters, and commutativity, if something is commutative, it means that it doesn't matter which order you do it in. But here, if it's anti-commutative, then the order matters. And so this means that A cross B is not equal to B cross A. However, it is equal to minus B cross A. So you just pick up a minus sign. Okay? It is also right-handed. Okay, so we always use right-handed coordinate systems. So that just means I hat cross J hat will give you K hat. J hat cross K hat gives you I hat. And K hat cross I hat will give you J hat. Okay, or you can remember this kind of circle, go from I to J to K, back to I. So I tend to draw this somewhere on my paper so I don't forget. Okay, and if you go in any other order, just again means you pick up a minus sign because it's anti-commutative. We can also take the derivative of a cross product of two vectors. And since it's a product, since cross product is a type of product, we really just use the product rule. So if you take the derivative with respect to, say, t of a cross product between two vectors, A cross B, here you just get the derivative of the first crossed with the second, so this is how you multiply them, plus the first crossed with the derivative of the second. Okay, and then the last thing is that cross products pull out perpendicular components and multiply them. So if you ever cross a product with itself, no components of these vectors are perpendicular to itself, so you get 0. So let's look at some examples of cross products in physics. Okay, so in physics, you typically use a cross product when you get to rotational motion, and you find that torque can be written as R cross F. And so if we were to put this into our 3x3 matrix to evaluate it, we would put our unit vectors at the top, and then we put the x, y, z components of our vector R and the x, y components of our force in the rows like I've done here. And then we'd find the magnitude of the torque as RF sine of phi, where phi is the angle between them. So you could imagine in 3D, you have a right-handed coordinate system, x, y, z. You had some vector r pointing from the origin up in some direction. It would have some x, y, z components. And then this is where you have some force being applied. It also has some x, y, z components. This is how you would find, say, the torque or the moment caused by this force about this point O, okay, or the origin. You can also express the angular momentum as a cross product, so R cross P. And so again, you would have I hat, J hat, K hat in your first column, Rx, Ry, and Rz in the second column, and Px, Py, and Pz in the third column. And this is how you would get your angular momentum. Okay, so now let's do a few examples where we actually calculate the cross product and use it to solve some problems. So in this first problem, we want to evaluate the cross product of the vectors A and B. Okay, so A cross B is just going to be the magnitude of A times the magnitude of B times sine of the angle between them. Okay, and so that angle is given to us as 65, and we're given the magnitude, so this is just going to be 6 times 7 times sine of 65. Or if you plug that in, that's just going to give you 38. Next problem, we want to evaluate another cross product of the vectors c and d, but now they're given to us in a slightly different configuration. So the cross product, c cross d, is going to equal the magnitudes of c and d times each other times sine of the angle between them. We'll call that phi. But this angle that's given, 140, is not the angle between c and d. If we want the angle between c and d, we need to draw the first vector, and then we need to start from the same point and draw the second vector. And then this is the angle that we're looking for. But if you continue this on, this is the angle that was given. So this is our 140 degree angle. And so in order to get phi, this is going to be 180 minus 140 degrees, or 40 degrees. So if we plug that in, we'll get the magnitude of c, which is 10, times 5, the magnitude of d, times sine of 40, and that's going to equal 32. Now, because sine and cosine are cyclical, you can get the same value for different angles. And so sometimes you can get the right answer kind of by accident using the wrong angle, because it's equivalent, because sine and even cosine are cyclical. If you always want to make sure you get the right answer in plugging in your cross product, always draw your vectors from the same point. So start from the same point, draw your first vector, go back, draw your second vector, and then the angle between them is going to be your angle phi. In the next problem, we want to evaluate the cross product A cross B using the distributive property. So to do that, we have our vectors written in Cartesian form. So we want to write 4i hat minus 7k hat crossed with 5i hat minus 4j hat plus 6k hat. So first we'll distribute our 4 to the second vector, and we'll get 4 times 5 I hat cross I hat, and then we'll get a minus 4 times 4 I hat cross j hat plus 6 times 4 I hat cross k hat. And then we will distribute our 7 to these three terms, and we get minus 7 times 5 k hat cross I hat, and minus and minus will be plus 7 times 4 k hat cross j hat minus 7 times 6 k hat cross k hat. Okay. Now if you notice, we got some I hat cross I hat, k hat cross k hat. You could have went ahead and crossed these out and sent them to 0, or just ignored them completely. But I went ahead and wrote them. And then I hat cross j hat, this is going to give you k hat. I hat cross k hat will give you a minus j hat. So again, remember I hat into j hat, into k hat, back into I hat. And then k cross I, that's in order, so that's j hat, and k cross j will be minus I hat. Okay, so now we just need to be careful and keep track of our minus signs. So here we're going to have the first term is 0, the second term is minus 16 times k hat, and then we get a minus 24 j hat. The third term we get a minus 35 j hat, and then minus 28 I hat, so all negatives. And now we just need to combine our like terms, and we get minus, and I'll put them in order, minus 28 I hat, and then minus a 59 j hat minus 16 k hat. In the last problem, we're going to evaluate the cross product A cross B using determinants. So we want to find A cross B, and I'm going to write this pretty big so I don't have to, so I can erase pretty easily. So the components of my first vector, the x component is -4, +3, and then -2. And then my second vector will be 8, -4, and -5. So this is going to equal, my I hat component will be first. I'm going to circle this and do the determinant of this guy. So this will be, actually, I'm going to put this in brackets so I can have some parentheses. So this will be 3 times -5. So again, going from top left to bottom right, minus a -2 times -4. So top right to bottom left. And then I'm going to erase this for my second component. Going to do j hat. So again, cross these out. And I'm going to get the determinant of this guy. So this will be minus j hat. And then -4 times -5. And minus a -2 times 8. Okay, now I want to do my last component. So that will be plus k hat, and it will be the determinant of this 2 by 2. So this will be -4 times -4 minus a 3 times 8. So you really have to be careful with your minus signs. And if we write all this out, this will be I hat times a -15 minus a +8, so -8 minus j hat. This will be a +20, and a minus a negative is +16, plus k hat. This will be minus and minus is +16 minus 24. And if we simplify all that, we get minus 23 I hat minus 36 j hat minus 8 k hat. So hopefully this gave you a good introduction to the cross product, and these problems showed you how we actually evaluate it in different ways, and so you'll be ready to evaluate cross products in your physics class. See you in the next video.